Ahoy hoy, I'm Planet Walk, and the reason why this headphone splitter isn't flying off of this cable is because of the centripetal force provided by the tension in this headphone cable. Essentially what that means, Dell, is that if you try and pull anything apart, there is a force acting against you that's keeping it together. And that force is not what you'd call a pushing force, is it, Dell? But anyway, today I'm going to address the claim that people should be just flying off the Earth if the Earth really was spinning at 1,000 miles an hour. So the first thing you have to ask is, why would flat earthers think this? The reason why they think this is because if you were to spin a ball with a whole lot of water on it really fast, then the water flies off. Their reasoning goes that because this ball that they're spinning is moving at less than 1,000 miles an hour, then because the Earth is moving at 1,000 miles an hour, all the water and people should fly off of it. Now, even though this claim has been addressed time and time again, I want to take a different approach to it. And yes, I'll even be using Flerf maths so that Flerfs can keep up. So the first question that needs to be asked is, why does water fly off a fast spinning ball? And to do that, I've got a whiteboard. This is going to be difficult, isn't it? So I'm pretty sure this whiteboard is bigger than Conspiracy Cats is. Anyway, the reason why water will fly off a spinning ball that's moving fast enough is because objects want to travel in a straight line. So if that's a water droplet, it wants to travel in a straight line. However, generally there are forces keeping the object attached to the spinning ball. So when there is enough force to keep the water droplet attached to the spinning object, the water droplet will follow a circular path. However, if the object is spinning fast enough, then there will be enough force for the water droplet to overcome the forces that are keeping the water droplet attached to the spinning object. Therefore, it will follow the straight path. Obviously, that is the simple explanation because it can get a lot more complicated than that, but I'm trying to keep this simple for the flat earthers. So when the water droplet has enough force to keep it attached to the spinning object, it obviously can't move in a straight line. It has to follow the circular path. But what it does do is it does exert a force called centrifugal force, which is in the opposite direction to the spinning object. So in the opposite direction to the centripetal force. Also, centrifugal force can be used to debunk the claim that water always seeks its level, therefore the Earth is flat. However, if you take a bucket, fill it with water partially, start spinning that bucket around, eventually the bucket will reach a point where it's upside down, and the water will still remain in that bucket. As long as you're spinning that bucket, the water will not try and conform to the level of the Earth. Instead, the water will just conform to the level of the bucket. So what this means is that an observer outside the bucket would look at the bucket, realize that it's being spun, and realize that it's actually not conforming to what level generally is. However, an observer from inside the bucket would go, well, this bucket isn't spinning, and would conclude that the water in that bucket is actually level. That is the difference between being on the Earth and going, oh, this cup of water is level, therefore all the oceans must be level, to being in space going, I can see upside down oceans. Anyway, let's get back to the claim of spinning balls at 1,000 miles an hour. So let's say we have a spinning object, right? This object will be spinning that way. And let's say there's an object that's attached to that spinning object by some kind of force. But all of a sudden, whatever force is keeping this object attached to this spinning object suddenly just lets go, right? And so therefore this object will continue in a straight line. If you were an observer on the spinning object, the object that detached would appear to be accelerating away from the spinning object. So the rate at which the detached object appears to accelerate away from the spinning object depends on two factors. It depends on the speed of the detached object, but it also depends on the size of the spinning object. But we can actually, instead of using the size of the spinning object, we can just simply use the curvature of the spinning object instead. So if your spinning object happens to be a sphere, that means that it has a curve to it. And any observer on your spinning object that is attached to the spinning object we'll have to follow the path of this curve. So, let's say that an object detaches, and you've also got an observer. So the object that detaches somehow would have to follow a straight path, right? It's a little bit bent, but I'm not 100% good at drawing straight paths. So just say it takes 2 seconds for your observer that's still attached to the spherical object to get to here. And it takes 2 seconds for the detached object to get to here. Well, this distance here can actually be approximated with drop. Now the reason why we can use drop is because an object that detaches from the spinning object will actually travel the same amount of distance as an object that doesn't detach from the spinning object. Now keep in mind that if you're doing some kind of professional work where you do have to work out centrifugal force, use the proper calculation for centrifugal force. Do not use the calculations that I'm about to use, because these calculations are just very close approximations that do work for something on the scale of the Earth. Also, for part of this, I'm going to be using Flerf maths. If you're doing any professional work, never use Flerf maths. Only use Flerf maths to argue with flat earthers. Anyway, with that out of the way, let's get into the maths. So first we need a value for how fast our object on the spinning ball is going. Flat earthers give us 1,000 miles per hour. Now the next thing that I want to do is I want to convert this from miles per hour to miles per second. So what we do is we take amount of minutes, 60, times amount of seconds, 60. We get 3,600. We have 1,000 divided by 3,600. And that comes out to approximately 0.28. So now that we've got the amount of miles per second, we need to calculate the amount of drop. And we're going to be using the formula 8 inches per mile squared. So now that we're using the formula that flat earthers just love to use, we've got to square 0.28. And 0.28 squared is 0.0784. Now all that's left to do is just times this by 8. Now 0.784 times 8 is 0.6272, but we're just going to use 0.63 because I can't be bothered, increasing the amount of digits beyond 2. So after all that, what this means is that after 1 second of not having anything attaching you to the Earth, you would move 0.63 inches away from the surface. Now, if we convert that to an acceleration, very lazily assuming that acceleration is all linear, we get an acceleration of 1.26 inches per second per squared. Now, this poses a problem for flat earthers because there's an acceleration pulling people towards the ground of 9.8 meters per second squared, much more than 1.26 inches per second squared. However, I'm not finished because the rotation of Earth actually isn't 1,000 miles per hour, it's 1,034.5 miles per hour. And we shouldn't actually be using 8 inches per mile squared, we should actually use the proper calculations. So this has been a lesson on do not use Flerf maths. Even flat earthers don't use this. So let's go through the proper steps this time, shall we? Instead of using 1,000 miles per hour, we're not going to use miles per hour. We're going to be using meters per second because metric is the correct way to do this. And the amount of meters per second that we're going to be using is 460 meters per second. And also, I did make a bit of an error earlier, if you caught it. I said that the Earth spins at 1,037.5 miles per hour. I wasn't taking into account something because it actually spins closer to 1,029 miles per hour. See if you can figure out where I went wrong. Anyway, using the Earth curve calculator, and we're not using the whiteboard, that's for Flerf maths. We're using the computer, right? So, metric, put in an eye height of 0, and we'll put in a target distance of 0.46 kilometers because that is 460 meters. Calculate, and we get 1.66 centimeters. Thought it would be a bit more than that. So yes, when you actually take the time to do the calculations, you find that the spin of the Earth wouldn't actually send people flying off of the Earth, because there's a 9.8 meters per second pull towards the Earth. There would have to be something much larger than that to send people actually flying into space. And let's be honest, the only reason why flat earthers say, oh, there's a 1,000 miles per hour spin at the equator that would send everyone flying into space, is because 1,000 miles per hour is quite a large number. They then go ahead and compare it to something like water flying off of a tennis ball when spun really, really fast, because that's easy to understand. This is a little bit harder. So hopefully everyone was able to keep up with that. But one thing that I want to say, because I think flat earthers are probably going to leave in the comments, oh, you're just brainwashed, you're just saying what you have been indoctrinated to believe in. The ideas that I came up with to calculate the centrifugal force in this video, because that's essentially what I did, they were ideas that I came up with myself. I actually used problem solving to work out, okay, this is a good way to approximate, well, I'm not sure if it's a good way, but it's a way to approximate the centrifugal force. If I was doing this all because I was indoctrinated, then I don't think that I would have done that. But anyway, leave a like and subscribe if you like that video. Leave a comment letting me know what you think. Also, happy Christmas, Hanukkah, Kwanzaa, or whatever holiday you celebrate. As always, a big shout out to my $20 or more patrons: TheSunExpress, What Jesus, Fight the Flat Earth, Holmes, Hugh Jarsz, M.C.Nutkin, Wolfie, String News 1, Ashpanash, Reynolds, Curvy New Yorker, and Syssiphus. If you want to support me financially, you can do so on Patreon, link will be in the description. But anyway, I will see you in the next video. Between you and me, thank you for watching. So 2020 is just around the corner, new year, new stuff happening, and maybe conspiracy cats will need to watch out a little.